Now we're on. Thank you. My name is Bruce Momjian. I work for EDB. I've been working with Postgres, as she said, since 1996. As I said in the panel discussion in the morning, I had time to do research into AI a couple months ago. And what's kind of interesting is that about 5 years ago, 6 years ago, I also took off 8 weeks and spent time studying security. So basically one of the ways I do technical leadership is I look for areas where the community needs technical skills, where we're lacking. And fortunately, because EDB kind of lets me do what I want, I tell my boss I'm going to take 6-8 weeks, I'm going to study this. The guy says, great. I buy a bunch of books, I read them, I watch a ton of videos, I look at a bunch of web pages, and eventually out comes a presentation. In this case, this is one of 5 security presentations, which are actually on my website. If you go there to that URL at the bottom of the QR code, that is my website, 62 presentations, 2,800 slides, 131 videos, 650 blogs, something like that. So there is a lot there. I will say a lot of people in India seem to appreciate that material. Actually, this is the country that appreciates it the most, which is exciting. But why did I write this talk? I wrote this talk because I felt like the security, setting up Postgres securely was not obvious sometimes. As you may know, security is like a fence, right? You build a fence. If you don't build the fence all the way around the property, what happens? All the animals come in the hole that you left, right? So to do security right, you have to basically protect the entire perimeter of your server. And that's exactly what we're going to talk about here. We're going to talk about different ways that your server can be attacked, different ways of protecting it. Postgres does have a very good reputation for security and has a lot of security tools. But again, it is kind of required for you to understand what those security tools do if you're going to be successful at securing Postgres. Okay. We are running a little bit late on time because of the photo and the room change, so I'm going to see if we can tighten up the time a little bit to get back on schedule, but I think we have plenty of time. So as I said before, when you're securing Postgres, you can't have any holes. And this is one of the fundamental problems with security. Like if you look at performance, you can have some queries that are slow and other ones are fast, and it's not a disaster. But with security, like everything has to be secure. If there's a little thing that isn't secure, you have no security, effectively. So that's why it's important to really understand the security, understand what your attack vectors are, and how can you protect them. And this is what this talk does. Again, slides are at this presentation at that URL there. Okay, so what we're going to talk about is a couple things. First, we're basically going to talk only about external attacks. So these are attacks that are coming in from outside of your server. All right, so things like the way you set up passwords, snooping, whatever, all these things are part of it. I do, again, have over 600 blog entries, and there's a security section in that blog website, and you can just see all the security blogs. So again, if you want more detail for the tier, that would be the place to look. What I am not going to be covering are internal attacks. Now, I could have a separate talk on that, but there is not time to talk about that. So things like permissions, SQL injection, application vulnerability, operating system, these are legitimate security problems, but not something I'm going to be covering here. Okay, so when people think normally of security, they think of authentication, like how are you doing authentication in the system. And what's interesting is there's some cases where some authentication is fine, some situations where it's not. We have to walk through, again, what are the authentication options and then what do they protect against so then we can understand that we're doing the right thing. All right, any questions so far? I like to take questions as I talk. Okay, great. So let's look at the way that Postgres ships the default permissions. Now, this is not necessarily the way you have Postgres. If you download it from an RPM, Debian, any of the packages, they might have different defaults, but the source install is effectively this. And what trust effectively means is that I trust everyone from this IP address or this IP block. Now, as you can see, this is the hba.conf file. We have separate columns for various specifications, but what it's saying is the first line is saying anyone who comes in on what we call a Unix domain socket. Windows has these as well, but it's called Unix domain socket. Anyone who comes in locally on a Unix domain socket, they're literally able to connect to any database as any user, and we trust them. Okay, now whether that's a good thing or not, it's up to you, right? Do you trust everyone on your particular machine? If it's a development machine, you probably do. If it's a production machine, you probably don't. Again, you can understand why you might want to use some of these and not others. The other two, again, related to TCP connections, which come from localhost. So these are a little different. First one uses Unix domain socket. The second one uses the TCP stack, but again, it's the same issue. Somebody coming in locally. And what this is also telling us is that nobody from outside can connect. Just, we don't have a line there. The line doesn't exist. They're not coming in, period, right? Now, this may be fine for you. This may not be fine for you. But again, this is the way it comes by default. Some of them, for example, I know Debian will change the trust so that it uses effectively an authentication method called peer, which allows you to send credentials through Unix domain sockets. I know I'm going a little crazy here, but there is a peer concept in Linux where you can send credentials across from one socket. Because you're on the same machine, you're saying who's on the other end of that socket. And it'll tell you who that is, and therefore you can know, okay, that I trust them or I don't trust them. So there's a whole bunch of cool stuff you can do in that peer idea. But again, it gets much more complicated. So the first issue, that security issue people are going to have is the sort of the go-to security option is password. Okay, now that's been changing over time as you see more and more two-factor authentication. You see more sophisticated capabilities. Our company actually uses YubiKey to do part of their authentication, which I do recommend. I have a whole bunch of YubiKey blog entries on my website where I kind of use YubiKey with Postgres. It's kind of cool. The password's kind of the normal way people are going to do it. And the normal way, when you use password as an authentication method, effectively what it does is to send the password in clear text across the network or across the socket, right? Now that may be fine for you. Again, particularly if you're doing Unix domain sockets, well, it's not really going anywhere. It's all on the same machine. Might be fine. You don't get the advantage of peer, so you probably should use peer if you have it. But if you're going across a network that you trust, then that may be fine. But if you're going across a network you don't trust, then that is not fine, because effectively that password is vulnerable to anyone using Wireshark or any of those networks tools. As you may know, it's very easy to get onto a network and turn your laptop into promiscuous mode, which is the concept where it'll effectively just display every packet it sees as it goes across. That's the way Ethernet is designed. It doesn't have encryption by design. There is IPsec, which does have permission, but by default, TCP/IP doesn't. So again, that is kind of a serious problem. We are storing the passwords in MD5 typically in the database, although I'll talk about Scram and SHA-256 in a couple minutes. But effectively, that's the way. We do store it encrypted. Another option, which is an older option, I'm not going to recommend, is called MD5. Effectively, what happens is we send a random salt. As you can see, unfortunately, my pointer does not work on this screen, so I just have to kind of pretend you know where I'm pointing to. But you can see that in the middle line, we're sending salt across to the client. The client is using that salt as part of the MD5 hash. And therefore, that allows, you can't see the username in clear text, but secondly, you also can't replay because the salt is random. But there is a problem with that. One problem is that when this salt was designed, and I was involved in that design back in I don't know, 2002, 99, something like that, we only got a 4-byte salt. Now you think, okay, that's 4 billion, how much replay are you going to have? Well, if you think of the birthday problem, if you've ever heard of the birthday problem in mathematics, effectively you get duplicates pretty quickly. It's just that because you're randomly choosing numbers, the chance of a duplicate happening is for over 100 or several hundred iterations is actually pretty high. So that's kind of a serious problem. Again, this is showing that the salt changes from one to another, which is everyone kind of gets, okay? But again, what most people are going to be using since Postgres 10 is not MD5. It's in fact Scram SHA-256. So Scram SHA-256, that's a combination of SHA-256, which is a better hashing algorithm than MD5. Plus you have Scram, which allows you to authenticate that it is basically a protocol that allows the remote side to prove it knows the password without sending the password. I'm not going to go into that, but effectively, most people are going to be using SHA-Scram 256, and in fact, Postgres 14, it's the default. Okay, so you might think, okay, I'm great. I'm not using MD5. I'm using Scram 256. The problem with the salt being too small, that's gone. So we fixed that problem. We're now storing the password with the SHA-256 in the server, so that's great. So effectively, we're thinking, okay, this is great. Things are wonderful. We can sort of stop there. Well, not really. Again, as I said, to have a secure system, you have to have all of the things around it secure. And effectively, you still have the problem that you're using a password. We can have people choosing weak passwords. We can reuse old passwords. And then we have the problem of brute force. People can be brute forcing those passwords if they're not complex enough and effectively breaking into your system. We do support things like LDAP, PAM, and SSPI, which again kind of handle some of those things, but it's not obvious. Any questions so far? Yeah, no, okay, great. Okay, so we still have some issues. Again, we have to have a secure setting around. So let's suppose that SHA-256 Scram is solving our problem. But even though we have authentication solved, we still are passing our data in clear text. So all the queries are going in clear text, and the results are coming back in clear text. So all my data is now snoopable by anyone on the network. All right, now that may be acceptable to you. It may not be acceptable, but you have to realize just because you get authentication done doesn't mean your security problem is necessarily solved. All right. So in this case, even though we've authenticated, queries are going in plain text, data's coming back, somebody can be snooping. All right. So people are like, okay, I know how to fix that. There's something called SSL, a secure socket layer. Goes back to the early 2000s. Actually, I think designed for not Firefox, but Mosaic. Goes back like really far. First browser, okay? And that's going to use AES 256 to encrypt the query and then encrypt the data coming back, all right? So now we have authentication solved, whatever we're using there, maybe it's Scram, and now we're using SSL. Okay, so we're encrypting the data going back and forth. Is our problem solved? And the answer it is not, okay? And the reason it is not is because it is possible for somebody in the middle to intercept the communication. If you're familiar with how TCP/IP works, there's something called an ARP request, where you're actually saying, I'm looking for the MAC address, the hardware address of a specific IP address. You send out the request to the MAC, the ARP reply comes, and now you know who to communicate through, what MAC address to send it to across the network. It is possible for somebody to basically reply before you do and say, I'm that IP address, and there is possible to do. So you have to be careful of somebody being in between you and your data, because effectively what can happen is that somebody can basically interfere with it. So here's a good one. This is kind of weird, but effectively imagine your database is down. This is a good man-in-the-middle example because it's actually really easy to do because your server's not answering for whatever reason. Maybe you're in maintenance. So all of a sudden, somebody says, I'm the server. You're like, really? Okay. And what's interesting is the server normally controls what kind of authentication you do. Okay? Remember I talked about the HBA file. It normally is going to say scram SHA-256, but it could say just password. And if your client is not sophisticated, it's like, oh, you want my password? Here it is. Okay? Unencrypted on the network, easily to record by this fake server, and then the fake server turns some kind of error like, oh, I'm down or something, and the person never realizes that their password's been attacked, been scooped up, and then once the real server comes up, person who's spoofed basically uses that stored password, gets into their server. Not a great thing, okay? Another thing we can do is basically, again, have a fake server, which in this case, the fake server isn't down. It's actually the server's actually up, but because of the way this thing is set up, you basically are using, it's connecting, and the fake server kind of intercepts you and says, okay, I want a password. It sends a password back, and you're done. Now the user realizes that I got an error, but they don't really know why. Okay, now this is much more realistic. This is what's called a pass-through attack. So in a pass-through attack, effectively what's happening is this fake server is acting as a proxy between you and the real database, okay? And you can imagine if you're going through multiple networks or you're going through the public internet to get from one server to another, it's very possible for a server in the middle to pretend to be you. There are routing tables and there are ways of sort of faking TCP/IP to pretend there's somebody else. And what happens is effectively the fake server, you connect, it says, I need a plain password. Client sends the paid password. And then what happens is the fake server sends it right to the real database. And then it runs queries, and then all these queries are going through the fake server. Okay? The client has no idea that they're going through this intermediary fake server. Fake server is seeing all the data. Fake server can issue its own queries. Fake server effectively has recorded the password. Okay? Kind of a serious problem. Any questions? Okay. So we can fix that in Postgres. We actually have a way of specifying what type of SSL mode you want. So there's various modes, and I'm going to explain what it is. But unfortunately, the default mode for SSL, and we've talked about this for years, is something called prefer. And what prefer does is effectively, it says, do you want, you say, I prefer SSL, and the person says, I don't have SSL, and the client just keeps going without SSL. Okay? So that's obviously it's not what you want. You can issue something called require, and in the require case, it's only going to use SSL. Okay? But the problem still is that you're still going through this fake server, right? So even though we're using SSL from the client to the fake server, it doesn't matter because it's like, oh, I have a really secure connection to the fake server. Well, who cares? The fake server is fake, right? And you're using SSL and you think you're safe, but you're not because the fake server is easy able to set it up. Now, what really the way you really fix that is something called certificate authorities. Now, I'm not going to go into certificate authorities. My blog has a lot of details about that. But what effectively a certificate authority is you have a certificate, as you can see here, on the server, okay? And then you have another certificate on the client. And as I said before, I have 5 security talks on my website. Actually, if you look in the security tab, there's 4 very detailed security talks, over 300 slides. And several of those do talk about how these certificate authorities work, how they are signed, how the security works. But effectively what happens is that if you specify the SSL mode as verify CA, you will only connect to a server which has a certificate which is signed by the same certificate authority as your local client certificate. So you basically have this certificates on both servers. There's a private part of the certificate and a public part. The private part is really the part you have to have on both ends, but the public part can be sent to anyone, okay? But effectively, you have to prove that the other end has a certificate that was signed by the same certificate authority as me. And that establishes trust. This is the way you go onto a website now. When you're using HTTPS, that verify CA is basically a requirement. Any HTTPS, it is going to verify that those certificates on the web server that you connect to are signed by some central certificate authority, and there are a dozen of them or more, which they are stored in your browser, right? And you're basically saying, is the website I'm talking to have a host, is their domain name have a certificate signed by one of the certificate authorities? And it gets very complicated, but it works great with the browser, and again, it works great here. There's another capability which does not require certificates, which is kind of newer to Postgres, newer as in maybe 4 years, called channel binding. And channel binding can be a little hard to understand, but effectively it's an extension of Scram SHA-256. What effectively happens, and again we have a little handshake here, is effectively what you're doing is you send a message to the server and you say, prove that you know my password. All right? Now it's not going to send the password back, but it is going to send a hashed result that proves that the person, the server at the other end of this connection knows your password. And once they've proved they know, once the server has proved that it knows your password, then you encrypt your password and you send it and you show proof that you know your own password. Make sense? Right? So the server is proving it knows your password, you proving that you know your own password, and now we can communicate. And it's impossible for somebody to get in the middle of this because effectively they can't send that reply back proving they know my password. Kind of cool. This is, again, technology that's only 5-7 years old. Yes, Pat, please. Does the client need to change in some way to do that is the question. Yes. You effectively would set, there's an SSL mode where you specify the channel binding. So what's interesting, Pat, is it's really remember I talked about the PGHPA and the servers controlling authentication? Well, in this case, it's really the client that has to specify it because the client is the one who wants to prove. If we allow the server to do it, fake server is going to just say, hey, we're great, you know? So in this case, exactly right. In the connection string, great point, you actually have to specify this channel binding, okay? And we did this about 6 years ago, very excited about it. It does make it easy to set up that type of security without having to go through a certificate authority, which a lot of people find confusing and hard to manage. This is a much simpler way of doing it. Okay. Another way of doing it, which I kind of love, is what we call certificate authentication. So in this case, instead of sending a password, you actually send a certificate and you sign that certificate with your private key to prove that is my certificate. I know it, nobody else knows it, and that's how I'm doing authentication to the server. So all of a sudden, we're not even using passwords anymore. All right? We're literally signing our own certificate, sending it to the server with a special code that it sends us, and that says, okay, I'm authenticating because I know my own password. I'm sorry, because I know my own certificate, and my certificate is signed by the same certificate authority there's some real benefits to this. For example, rotating authentication keys is real easy now because the certificates have an expiration date. You can swap out certificates without having any hiccup in authentication. So that's a really cool capability. Again, we have a URL here at the bottom. Okay. Any questions? Okay. Right. Okay. Let's just shift gears a bit. We've gone through the problem with passwords. We've gone through the problem with SSL. I've explained the value of certificate authorities. We've talked about channel binding. But let's talk about some other options and other cases where we can be attacked, right? Like we just not in connections. And one of them is effectively data theft. So the story that I have for that one is when I was a consultant in the 90s, I used to work at a law firm, a bunch of law firms. I used to go to different law firms. And I remember being in the server room once, and there's a box in the corner of the server room with backup tapes. And I was with a guy named Herb, and I said, Herb, why are you leaving a box of backup tapes in here? Like, it doesn't look right. It's kind of sloppy. I don't know. It just didn't look like it belonged here. And of course, the server room was secure. Had a key lock and so forth. Key code to get in. He says, if somebody just picks up a backup tape and walks out of the law firm, they got all our data. And I'm like, oh, that's a good point, Herb. I didn't think of that. So that's why the box was in the server room, right? So one of the other ways, obviously, that you can have theft is effectively the idea that somebody steals your storage. Now, there are some solutions to that. For example, encrypted storage, encrypted drives, encrypted backup tapes. But it's something to consider. Don't just look at the connection capability. Think broader about what your attack possibilities are. Okay. One way, of course, is disk volume encryption. Postgres does not support disk volume encryption itself. I have a blog entry from about 3 weeks ago talking about TDE and the fact that we probably will not be implementing TDE in Community Postgres, although I know there are a large number of vendors who have implemented it, so that's good. I know Percona and Postgres Pro, EDB, all have ones. I'm trying to remember who else. Fujitsu and Crunchy and Cybertech. There you go. So again, there's a lot of vendors who are creating TDE implementations, and that blog entry explains why we don't do it. What we do support, obviously, is encryption at the operating system level. So encrypted drives, encrypted storage is pretty standard for most operating systems. That is one way of preventing theft of your data media. Another option which we should be aware of is basically column encryption. Postgres does a really good job with this. There's a lot of capabilities. There's PG Crypto. There's something called PG Sodium, which is a crypto sort of plugin extension for Postgres. Probably the simplest case here is a case where I'm effectively encrypting only a single column in my database. And again, very easy to do. PG Crypto makes that very easy. If you read my blog entries, the complexity is where do you store the key, right? We have the capability to encrypt it real easy in Postgres. How do we store the key? How do we make sure that effectively this encryption is done so the key is not also visible to an attacker? And that's one of the reasons I think the YubiKey concept, the hardware encryption device concept comes in. I have some examples of that. PG Sodium is another way. I think I created a little module myself that does it, but PG Sodium is probably a better sort of solution client side, I believe, to do this kind of encryption across the wire. Okay. And again, as I said, the problem is where to store the key. If you store the key on the server, well, if they steal the server and the key comes with it, and it's not really that great. Another idea is to have some kind of encrypted key server where the server connects to an encrypted server, and then it basically grabs the key and it refreshes it every so often. So effectively, if the server's stolen, it doesn't have access to the crypto server, and therefore it can't you can't access the data. That's one option. Another option is to put the key on the client. And that's kind of creative because effectively the server doesn't know any idea what the data is. It just has the data stored. Although the problem becomes effectively the client's going to be more complicated because the client has to do the encryption and decryption. And then secondly, indexing becomes difficult because at the server level, all you see is like a blob. You don't see any data. You can't index it. It's hard to say where client name equals whatever. Well, it's just a binary. You can't. So again, there are some downsides to doing the encryption on the client side. I'm not saying it's wrong, but you have to realize that can get complicated. Again, another idea in this case, we're sending the data. In this case, we have the key, but we're sending the data and the key to the server. This is somewhat risky because we're sending the key across the network. A more traditional way would be to encrypt it on the client itself before you send it. And therefore, again, clients are more complicated, but you're going to have the issue where you now have to decrypt it on the client. Okay. The coolest way, as I said before, is something a hardware security token. These are very popular, where effectively the hardware security token can be taken out of the server, out of the client when it's not being used, and then put into the server when you want to use it. Typically, they require you to type in a PIN, potentially, to unlock it. I have actually a little YubiKey stuck into my laptop, and also you may need to touch it to make it active. So again, there's these really interesting ways that you can do this. At the US government level, there's something called a CAC card, which is actually a PIV card. I'm not sure how many are familiar with that, but the concept is that effectively you either have a YubiKey style USB connector, or you literally have a credit card with a little chip on it, very similar to what you'd use for your standard credit card where you have a chip and pin. And you stick it into a device connected to the computer, and then when you're done, you pull it out. Frankly, in more modern, non-governmental cases, a USB connection is an easier way to do it, and there are some capabilities in USB that you can't do on a card, so it's kind of cool. Okay, questions? Let me take any questions. See what we have here. Yes, sir.
Hello. So we talked about not revealing the plain text password through the connections, but what if I don't want to store plain text passwords in configuration files, for example? If I want to connect my application, I store the DSN string, and there it is there, the plain text password. I don't want to store it as plain text password. Maybe add some mechanism where I obfuscate the password and then let the server deobfuscate it and.
Right. So we don't store clear text passwords in the server ever. By default, we're gonna hash those. So we're never storing the clear text in the database.
Yeah, I mean MD5 and all that is fine, but still there are clients who are nervous about storing it. I remember there's one client where they are applying their own mechanism to obfuscate the password, and then there's another binary which is deobfuscating it while making the connections. But the problem is that the binary exists on the same server. So I mean the script is on the same server. So if like we talked about key on the server, any attacker gets the access to that and it can easily decrypt it and.
Yeah, so you're right that we're using SHA-256, but that effectively is a way of connecting, is what you're saying, I think. In those type of cases, you're better off using something like a PAM or an LDAP, where you're storing the password in a separate place, and therefore they're never on the server. Yeah.
Yeah. Okay.
Yeah, or Kerberos. Yeah. Unfortunately, I am out of time. We're gonna get back on schedules because, again, I started late because of the stuff. I'll be here for the rest of the day, so if you have any questions, feel free to ask me. Thank you very much.
Thank you, Bruce.